This is just a review of all of the different ways that we have calculated both the enthalpy and the entropy for processes such as heating or cooling, for compound formation, and for reactions. So just to sort of make sure that we understand the different equations that are used in each of these cases, and also what the symbol delta actually refers to in the equation. First, at delta H and delta S for heating or cooling, and I'll sort of write this as for heating, but obviously if we reverse the temperatures, it would be for cooling. So we have this delta, and we want to first sort of ask, what does the delta mean, right? So what are the before and after states? So in this particular case, the before is just the system at T1, and the after state is the system at T2. So as we go from T1 to T2, this is the change in the enthalpy of the system or a change in the entropy of the system. If we have a phase transformation, we have to remember to include that in our calculation. If not, we can write the expression for the change in enthalpy as the integral from T1 to T2 of NCP dt. Right? If we do have a phase transformation in there, then instead of writing T2 there, we would write of the T transformation. This would be the CP sort of the low temperature phase, and I'll just put an alpha here to indicate that. And then we'd have to add on the delta H of the transformation. So this could be a solid-solid transformation or a melting transformation. And then the integral from the transformation temperature to T2 of NCP of the second phase dt. So this is how we would find the enthalpy change just associated with heating. In the case of an entropy change, we use essentially the same approach. So we're integrating T1. Let's assume that we still have our phase transformation present. So this is now NCP divided by T dt. For a change in entropy that occurs at the transformation temperature, we can write that as delta H trans divided by the temperature of transformation, and then our second integral of NCP of the second phase, let's say divided by T dt. So in terms of sort of how these look, just sort of as a reminder, right, we plot H versus T. This is 0 at a reference temperature of 298. We might have some transformation here. So this could be due to melting or a solid-solid phase transformation. Right? And enthalpy is increasing with increasing temperature, and we would have a similar plot if we were looking at entropy versus temperature with some kind of step in there. Okay, so that's delta H for heating. Next, let's consider delta H and delta S for compound formation. So again, we want to first ask, what does the delta mean? What's the before and what's the after? So the before state in compound formation is just the reactants in whatever state we say that they're in, basically, or at whatever temperature they might be at, and the after would be the product. So to make these calculations, we need to go from the temperature that we're interested in down to 298, so delta HF, so this is as a function of temperature. So from T to 298, and this is the sum over the reactants, because we're starting with the reactants at the temperature of interest. And so we have the sum of all the reactants and Cp dt. So we go down to 298, then we can look up the tabulated value of delta HF at 298. And so we sort of let the reaction occur at 298, and then we integrate from 298 to T of NCP dt, and this here is for the product. And we can use a similar approach for delta S. So we have the integral again from T to 298, the sum of the reactants. Now we have NCP divided by T dt. What we need at 298 is the delta SF at 298. And we'll talk in a minute about how we find this, but this comes from the absolute entropies, and then we integrate from 298 to T of NCP over T dt. And this again is for the products. So that is how we calculate our enthalpies and entropies of formation. Just take a quick look basically at the difference between absolute entropy and the entropy of formation. So just in terms of symbols, absolute entropy is this S with this little superscript, which indicates that it's the absolute entropy, versus the entropy of formation, which looks like this. If we want to calculate the entropy of formation, and we can keep this up here, this is just saying that everything is pure. We do this in the following way. We sum for the products, N, so this N is the stoichiometric coefficient, N times their absolute entropies, and then we subtract off the absolute entropies of the reactants. This is one way that we can find delta S of formation. If we know the Gibbs free energy of formation and the enthalpy of formation, which are tabulated, we could also calculate this in the following way. Divided by negative T down here. So these things here are tabulated. You could find those. This is tabulated. This is tabulated. These are usually not tabulated, and so you need to calculate it using one of these two approaches. Okay, so the next kind of that we know how to calculate is the delta H of a reaction. And delta S of a reaction. So let's think about what is this delta. So what are the before and after states? So the before would be the products at the temperature, not the products, it would be the reactants. At the temperature of interest, and the after state would be the products at that same temperature. So if we want to calculate delta H of the reaction at some given temperature, let me put this in here. So this is not multiplying T. This is just indicating that we're doing this at some temperature. We sum over all of the products, N times the delta H of formation at that particular temperature, and we subtract off the sum over all of the reactants, N times delta HF at that particular temperature. Now if we have just pure elements, then delta HF is 0. If you don't know delta HF at this temperature, then you use the approach that we just talked about to determine this as a function of T. And we could use a similar approach for entropy of a reaction. So the delta has the same, but we can calculate delta S of the reaction either in that same way. So delta S of the reaction at some T, we can get either by summing over the products and delta SF at T, and then subtracting off basically that same thing for the reactants. You can also do this, though, with the absolute entropies instead, right? So we could instead write this as the product, so this would be N, and then the absolute entropy. So whichever is easier to calculate the entropy change, you can do it in that way. So that's the summary of how we use all of these different equations for calculating changes in enthalpy and changes in entropy.